Alright, last time we had talked about using duration, modified duration in particular, to estimate changes in price. And we noticed that the price was always underestimated when we used modified duration. And that's because duration is based on the first derivative or the tangent line approximation. So, for example here, say that we've got a particular interest rate, and this is on the price yield curve, P versus I. And then we change that interest rate. This is going to be I0 plus delta I, so that we've had a small change in interest rate here, delta I. And then we wanted to see what would happen to the change in price. Well, at I0, if we go up and over, this is going to be the actual price at the interest rate I0. And then at I0 plus delta I, if you go up to the point B, which is on the price yield curve and over, that's going to be the actual price at I plus delta I. And that's what we're trying to estimate. Well, I0 plus delta I. And what we did was we used the tangent line approximation. So here's the tangent line at the point I0, P of I0. And you follow that tangent line down until it intersects the vertical line at I plus delta I. That's at point A. So in other words, you go from I0 plus delta I up to the tangent line and over. And that was the value that we got from modified duration. So notice that this value here is strictly less than the actual value P at I0 plus delta I. And that's because the tangent line, no matter where you put it along this curve, the tangent line is always below the curve. So that means whether you've got a positive change in interest rate or a negative change in interest rate, when you use the tangent line here to approximate, you're always going to get a value that's less than the actual value. And in fact, the farther that you get away from the point of tangency, the more your estimate is going to be below the actual value. And in fact, the reason that the tangent line is always below the curve for the price yield curve is because this curve is concave up. And in fact, that's actually an alternate definition of being concave up, is that the tangent line is below the curve. So just a little note here. Tangent line here below the curve actually corresponds to the curve being concave up. And then as a result of that, tangent line always underestimates the new price. Which is what we're seeing here. The value on the tangent line is strictly less than the actual value. So we want to correct for that. And we're going to use what actuaries call convexity. And what we are calling concavity in calculus is actually what actuaries call convexity. So when they talk about convexity, they're referring to the curvature of the price yield curve. And just like in calculus, this curvature is controlled by the second derivative of the price, P double prime. And in particular, just like in calculus, when P double prime at I, here our independent variable is I, when that's greater than 0, then our curve is going to be concave up at that point. Now, remember with duration that we formulated our concepts in terms of relative amounts, that is, as a ratio out of the total. And we're going to do the same thing with convexity. Our definition of what we'll call convexity, which is also sometimes called modified convexity, is that it's the ratio of p double prime over p, where our prime here means derivative with respect to I. So in other words, convexity, just like duration, is a relative measure. So, okay, so how does using convexity or using the second derivative improve our estimate? Okay, well, let me ask you to recall the Taylor series for the function f at x equals a. So the Taylor series, if you have a function that has enough derivatives, in this case infinitely differentiable at f equals a, then that means that you can represent f of x by its Taylor series in most cases. F at a plus f prime at a times x minus a plus f double prime at a over 2 factorial x minus a squared, etc. So the order of the derivative is the factorial on the bottom, and it's also the exponent on x minus a. Now if we take this quantity x minus a and we call that delta x, then we can represent this as f of a plus f prime of a delta x plus f double prime at a over 2 factorial delta x squared, and so on. Well, we want to make a little bit of substitution here so that we can use the Taylor series for approximation of a function. So assuming that we have a Taylor series representation for the function, if we do the substitution x for x plus delta x, so wherever there's an x up here all the way through, we're going to plug in x plus delta x, and for a we're going to substitute x, so all the way through here we're going to substitute x for a. Then this series becomes f at x plus delta x, so this is an increment added onto x, could be positive or negative increment, is f at x, and that's this x value, plus f prime at x delta x plus f double prime at x over 2 factorial delta x squared, and so on. Now if we stop this series at the second order term, so we only go up to the second derivative, then we get what's called a second order approximation. So we get a quadratic function. And that quadratic function looks like f of x plus f prime of x delta x plus f double prime of x over 2 factorial, which is just 2, times delta x squared. Now, just to get an idea of what this is doing for us by approximating the original function with this quadratic equation, I take a familiar function, log x. This is y equals log x, ln of x, natural log, is the dark curve here that goes off to minus infinity as you approach the y-axis, and then it's in between this straight line, which is the tangent line or the first order approximation. And when we did Taylor series, we called that T1, which is you take the Taylor series and you only go out to the first term. The first derivative. So that would be the first two terms here. So f of a plus f prime of a times delta x, or times x minus a. So that's just the tangent line. Okay, so T1 is just the tangent line. And then if you go out to the second derivative term, and this should show up as a dashed line on your notes, and that's actually here. This is a parabola that is what we call T2. So the subscript here, the T is standing for Taylor series, and the subscript is telling you how many derivatives you're taking. So the order of the derivative in the last term. So this right here is T2 in general. This is T2, a quadratic equation that comes from the Taylor series expansion for log x. Now if you zoom in on the point of tangency, and here I use the point of tangency to be 1, 0. So if you zoom in on that point right here, then you see that, okay, the tangent line here, this function is concave down, so that means that the tangent line is always above the curve. So then the tangent line is always going to overestimate the function value if we use the tangent line. However, if we use the second order approximation, T2, we get a better estimate. Notice here that T2 is below T1. That is, the quadratic approximation is below the linear approximation. So it went in the right direction, so to speak. And here if we zoom in on the point, the darker curve here in the middle, this is y equal ln x. And then the tangent line is here, so it's t1. And then the quadratic approximation, the second order approximation, t2, is right here. And then notice that for any point that you take, so let's say that we pick a value x that's right here, and if we go up to the functions from x and over, what we're saying is, okay, well, here's the actual function value that we want to approximate with the Taylor series. We could either approximate that with a tangent line, which is going to be right here, or we could approximate with the second order approximation, the quadratic approximation here. And notice that the value, the function value that we get from t2, the second order approximation, is closer to the actual function value than it is if we use the tangent line. And that will generally be the case, that our second order approximation is always going to be better than our first order approximation. Okay, and this isn't the curved line here, the quadratic is not showing up as a dashed here, but it should show that way in your notes. But here the general note is, note that T2 approximates better than T1. So this approximates y equal ln x better than T1. So that's what we're after, is that second order approximation. Okay, so let's change this over to our pricing function. So instead of y equals f of x, this is going to be y equals p of I. Okay, so if we just make the substitutions for the variables, instead of x plus delta x, this is I plus delta I. That Taylor series looks like p of I plus p prime of I delta I, p double prime of I over 2 factorial delta I squared, etc. And then that'll be approximately equal to the second order approximation. So just chop off after the second order derivative. And so all the rest of these terms, that's going to be our error in the approximation. And then I did a little bit of rearranging here. So the p of I stayed the same, p prime of I delta I stayed the same, but I took 2 factorial on the bottom as just a 2. I brought that out in the front as a 1/2. And then p double prime of I delta I squared. Okay, so now we're going to do a little bit more work with this approximation. So the price at this new value, I plus delta I, so plus some increment in the interest rate, we want to see how that changes price, is going to be approximately equal to the second order approximation here. And then what we would like to do with that is we'd like to write it in terms of relative measures, okay, because modified duration and convexity are relative measures. So inside here I'm going to divide this term and this term by the price, p of I. Okay, so I divided by p of I here and here, and then I multiplied on the outside to compensate. So all I did was multiply by 1. And you can double check, if you multiply this p of I back in times each term here, then these guys would cancel out and you get back to this expression. Okay, but remember that modified duration is the negative of p prime of I over p of I. So p prime over p is the negative of modified duration. Okay, so I'm substituting p prime over p is the negative of modified duration right there. And then p double prime over p, that is, that quantity is going to be defined to be convexity. Okay, so this p double prime over p, that's going to be what we call convexity. 1/2 I brought along, delta I squared I brought along, and then our price on the outside. So our new approximation here is going to be p, and then this is the approximation that we did previously. We added negative modified duration times the price times the change in interest rate. And now from the convexity term, that is the relative rate P double prime over P, we get this additional term here, 1/2 times the convexity times delta I squared, and then times the P of I, because this will come in times each piece. So this is the term that we got before, and this is our new one. Okay, so this is if you want, a correction to the first order approximation. So now if you look at the first line up here on the left and the last line on the right, if you take this P and bring it over as a negative, then you'll have P of I plus delta I minus P of I. Here I've written P as P of I. That's change in price. So then the change in price is just going to be these terms that are left here. So negative mod D delta I plus 1/2 convexity delta I squared P of I. Here I again factored out the P of I. I guess actually if you look at this line here, bring this guy over as a negative, then you get this line. So this shows us how to approximate the price at a new interest rate, given a change, small change in the interest rate. And then this shows us how to approximate the change in price. So depending on what you want, you just do a little bit of manipulation there. Now, one thing I want you to notice is the following here. Before, when we approximated changes in price, or when we approximated the price using the tangent line, we always got an approximation that was lower than the actual value. All right, and that's because the price yield curve is concave up, so the tangent line is always below, so the tangent line approximation is going to be below the actual value. So when we use convexity to correct this, we'd hope that it's going to increase the value of the tangent line. And that's exactly what happens here. Notice that here, this is our starting price. This is the first order approximation. Okay, that's the tangent line approximation. Actually, that would include the P. So P minus mod P delta I. That was our first order approximation using the tangent line. And then notice that delta I, for any change in interest rate, positive or negative, that gets squared. So this quantity is greater than 0. And then our price here is also greater than 0. And our convexity, okay, well, convexity, remember, is the same thing as concavity, and this curve, the price yield curve, is concave up. So convexity here, the second derivative, is concave up. So, I'm sorry, the second derivative is positive because the curve is concave up. So this is the second derivative. This is P double prime, and it is also greater than 0. Well, actually the convexity is P double prime over P, but both of these quantities are greater than 0. The second derivative is greater than 0 because it's concave up, and then price is always greater than 0. So we've added a term on that's positive, so we're going to be correcting our first order approximation in the right way by moving it up closer to the actual value. Now, if we represent the price as the sum of the, remember price is the present value of the cash flow, so we can represent that as the sum of cash flow at time t times v to the t, so discount factor just bringing everything back to time 0, then we can actually derive an expression for convexity using the price as the present value of the cash flows. So remember that if we take v to the t and take the derivative of that with respect to I, so prime here means derivative with respect to I. So remember that v is 1 over 1 plus I, or 1 plus I to the negative 1. So v to the t is going to be 1 plus I to the negative t. That's negative 1 to the t power to a power, so we multiply. So we're doing a derivative here of a function to a power. So to differentiate, the exponent comes down in front, minus t, keep the inside the same, decrease the exponent by 1, negative t minus 1. And then if you factor a negative out of this exponent, you get the negative of t plus 1. So everything else is the same. So negative t 1 plus I to the negative of t plus 1. And then 1 plus I to the negative 1 power is v. So if we put v back in, we get negative t v to the positive t plus 1. The negative exponent went along with the 1 plus I to make it 1 over 1 plus I. Okay, so the derivative of v to the t with respect to I is negative t v to the t plus 1. Okay, we're going to apply that here to the formula for p of I. So if we want to find p prime of I, what we'll do is take our formula p of I and just differentiate term by term. These cash flows here, those are constants. They may be different cash flows at different times. Most of the time it'll be a constant. But this quantity down in front of there, that's just going to get multiplied by the negative t out in front. So our p prime here is going to be the sum of, and actually why don't we take this cash flow here and kind of move it on the other side of v to the t and just take the derivative of v to the t. So the derivative of v to the t is going to be minus t v to the t plus 1. Okay, that's by this formula. And then times that cash flow at time t. And then if we want to do, this is a multiplication, and then if we want to find an expression for p double prime, then we do one more derivative. So another derivative means that this exponent is going to come down in front along with another negative sign. So this is going to be the sum of t times t plus 1. So it would be negative t times negative t plus 1, which will be positive t times positive t plus 1. Two negatives making a positive. And then v to the t plus 2. So you increase the exponent again. And then times cash flow at time t. So there's an expression for p double prime. So then convexity, by definition, is p double prime over p, which is going to be the sum of t plus 1, v to the t plus 2, cash flow at time t. That's this expression for p double prime. And then divide by price. Okay, so sometimes this formula will come in handy if you're asked to compute the convexity for a particular investment. So let's look at an example, put some of this stuff to work. So we've got an investment asset that's going to provide some cash flows of $5,000 in 1 year and then $10,000 in 3 years. So if we draw out a time diagram here, time 0, 1, 2, 3. So at time 1, we are going to have a cash flow of $5,000. And then at time 3, we're getting a cash flow of $10,000. And then $20,000 in 5 years. Okay, 4, extend this out a little bit farther, 5, $20,000. So those are the cash flows generated by this investment asset. And it's priced at 4% effective annual rate. We want to compute the following: the price of the asset, the modified duration, convexity of the asset, the price of the asset using only modified duration, so that we had done previously, and that's if we had a small interest rate change to 3.8, and then the price using modified duration and convexity. So I want to see how much convexity corrects our approximation with a change to 3.8 again, and then compare those to the exact price at 3.8%, and then look at what is a better estimate and why. Okay, well first let's price the asset. So the price of the asset is just going to be take the cash flows back to time 0. So you sum up cash flow at time t times v to the t is bringing it back. So we've got a $500 cash flow at time 1. That's going to be brought back by v. So this is going to be 5,000 v plus, and then we've got a $10,000 cash flow, and that is coming back 3 periods. 1, 2, 3, so it's going to be 10,000 v cubed. And then we've got a $20,000 cash flow that's got to be discounted 5 periods, so that's going to be 20,000 v to the 5th. So if we plug in our discount factor, which is 1 over 1.04, because the effective rate here is 4%, so I equals 0.04. And we do the calculations, we get 30,136.20. So that's the present price of our asset. Now let's find the modified duration of the asset. Well, first we have to find MACD. Okay, and remember that MACD is the sum of the cash flows weighted by the time or the duration of each cash flow divided by the sum of the present values of the cash flows. So we take the present value of the cash flows modified by or multiplied by duration because they're weighted by the duration. So on the top here, this is going to look like the present value of the first cash flow is 5,000 V, and that was occurring at time 1, so that's times 1, plus second cash flow present value is 10,000 V cubed, and that gets multiplied by the duration, which is 3. And then the last cash flow is 20,000 v to the 5th is the discount factor that gives us the present value, and that happens at time 5. So there's our numerator. And then our denominator, this is just price. Okay, and we already figured that out. That's the 30,136. So we don't have to do that calculation again. So now all we have to do is plug in our discount factor to get a numerical value for this. And I did that here. So 1 over 1.04, 1 over 1.04 cubed, and then 5th power. And we get a Macaulay duration of 3.77189. And then remember that modified duration is just V times MACD. So we just take that discount factor 1 over 1.04 and multiply it by our 3.77189, just comes down here, and we get a mod D of 3.6268. So there's our modified duration. Okay, next up they want us to compute the convexity. Okay, so by the formula that we derived up above, convexity is the sum of t plus 1, v to the t plus 2, cash flow at time t, divided by the price. So this is on the top here. Remember, this is p double prime. That was our expression for p double prime, and convexity is p double prime over p. Okay, so we've got to sum this up for the 3 cash flows that we have here. So for that first cash flow, get our time diagram showing again here. So that first cash flow happens at time 1. So the first time we have a sum here is when t equals 1. And that term is going to be 1 times 1 plus 1 is 2. And then v to the 1 plus 2 is going to be 3, v cubed. And then the cash flow at time 1 is 5,000. And then the next term that we have is going to be here at time 3. And so that's t equals 3. So this is going to be 3 times 4 times v to the 3 plus 2, 5. So notice this pattern here, 3, 4, 5. So that'll always happen. And then the cash flow at that time was the 10,000. And then the next cash flow occurs here at time 5. So that last term is going to be 5 times 6 times v to the 7th. And then times the 20,000. And then we are dividing that all by our price, which again we figured up here, 30,136. And so now we just need to, I did a little bit of simplifying here. 5,000 times 2 is 10,000 here. Put in our discount factor of 1 over 1.04. 10,000 times 12 is 120,000. 1 over 1.04 cubed, I'm sorry, fifth. And then 20,000 times 30 is 600,000 times v to the 7th. And then divide by our price that we already know, gives us a convexity of 18.6975. So there's our measure of convexity. Okay, next up, what we want to do is price the asset using only modified duration. Okay, only modified duration. So remember how we did that was we approximated the change in the price. That was negative mod D times P times delta I. And let's see here. Mod D we calculated. That was 3.6268. So negative mod D here is going to be negative 3.6268. And then our price, that means the price at the initial interest rate I is going to be the 3136.20. I forgot my 20 here. And I forgot my 20 cents there. And then times the change in interest rate. And the interest rate goes, the rate changes from 4 to 3.8%. Okay, so it goes from 4% down to 3.8%. So that's a decrease of 0.2%, which is 0.002 as a decimal. So our delta I is negative 0.002. And if you do the calculator work there, you get 218.60. So then our new price here is going to be the 3136.20. And then our change in price is positive here. So this is plus 218.60. So we add that on. So we get a total there of 3354.80. If we do the calculator work. And then hold on just a second. Does this make sense? Our interest rate changed from 4, it went down to 3.8, and interest rates vary inversely with the price here. Okay, so our change in I was less than 0. Okay, our interest rate went down. That's going to mean that our price increases. Okay, and our price did go up. It went up $218. Okay, so that makes sense. All right, next up we want to use using the modified duration and convexity. We want to estimate the price. Okay, so what's going to happen here is that we need to add the 1/2 delta I squared P times the convexity to the estimate that we have right here. So in other words, we've already done part of the work here. So we've done this much here. We've got the first order approximation or the tangent line approximation. So in order to get the approximation including convexity, we just have to add on this term here, which is 1/2 delta I squared P times convexity. And that's what we're doing here. We want to add on that term to our previous estimate. So let's figure what that correction is. So 1/2, and then our change in I is negative 0.002. So negative 0.002, and that gets squared, times our price, which is the 3136.20. And then convexity, our measure of convexity was right here, 18.6975. And if you do the calculator work here, you will get $1.13, rounded to the nearest penny. So what that means then, this is added to, okay, our previous estimate. So that means that our new price here is going to be the previous estimate, the 354.80 plus the $1.13. So then our new price is going to be $33.55.93. Just adding on that $1.30. Okay, part F said to compute the price, the actual price at the the new interest rate. So price is the present value of the cash flows, except now our discount factor here is going to be at 3.8% instead of at 4%. So we're still going to take that $5,000 cash flow at time 1 and discount it with V to the first power, and the $10,000 cash flow at time 3 and discount it with V cubed, and then the $20,000 cash flow at time 5 and discount it with V to the 5th. Except now our discount factor is 1 over 1.038. So if I plug that in all the way across and do the arithmetic or the calculator work, we get 30,355.93. And notice that our exact price, that agrees with our second order approximation. So which estimate is better? Well, definitely, estimate E is better than estimate D, than using mod D only. We were off by $1.13. In fact, this estimate is good within a penny. So, but theoretically, estimate E should be better because it adds the convexity term, and that offsets the underestimate that's given by only using modified duration alone. Okay, because notice here the 33.54, that underestimated the actual price, which was 33.55. So the convexity added to that and corrected that. Okay, in the next example, we're asked to determine the convexity of a 5-year, 1,000 par bond that's got 4% annual coupons if the bond yields an effective interest rate of 6%. Okay, so our effective annual rate is 0.06. So I equals 0.06. And this is set up as a multiple choice. All right, well, remember that convexity is P double prime over P. And then recall our differentiation formula, that the derivative of v to the t with respect to I is negative t v to the t plus 1. Okay, well, let's first figure our price in the denominator here. So 5-year 1,000 par bond with 4% annual coupons. So times 0, 1, 2, 3, 4, and 5. Got payments at times 1, 2, 3, 4, and 5, and then maturity at time 5. So it's a 1,000 par, 4% annual coupon, so those are going to be $40 payments here at times 1, 2, 3, 4, and 5. And then we're going to get our redemption value back. This is going to be redeemed at par since it has not told us otherwise. Okay, so all this stuff we bring back to time 0, that's the price of the bond. Well, if we take this constant annuity of $40 for 5 years and bring that back to time 0, that's just going to be 40 times A angle 5. Okay, that'll be the present value of the coupon payments. And then bring the redemption value 1,000 back with a v to the 5th discount factor. So plus 1,000 v to the 5th. And then if we do the substitution here with v equals 1 over 1.06, our discount factor here, 1 over 1.06, then you get a price of $915.75. Okay, now let's write a more general expression because we don't know how to differentiate this A angle 5 because we want to write P just in terms of V, and then we want to do derivatives to get to P double prime and then look at the ratio P double prime over P. So if we just look at these guys individually here, then P can be expressed as 40, that first coupon payment brought back 1 period, so with a discount factor of V, plus the second coupon payment, 40, brought back with V squared, plus third payment brought back with V cubed, plus the fourth payment of 40 brought back with V to the 4th, and then at time 5 we get the last coupon and the redemption, so 1,040 that's brought back with V to the 5th. So that's the price of the bond in terms of V. So then P prime, we can just use our derivative formula here. So this exponent is 1, so that's going to come down with a negative sign. This will be negative 40, and then you increase the exponent, so v squared. Negative 2 times 40, so that'll be negative 80. Increase your exponent, v cubed. Negative 3 times 40, minus 120. Increase your exponent, v to the fourth. Negative 4 times 40, negative 160. Increase your exponent, v to the fifth. Negative 5 times, this should be 1040 here. Because a total of 1040 is brought back. Negative 5 times 1040 is negative, let's see, 5,000, 5 times 40 is 200, 5,200. And that gets a factor of v to the 6, because we're increasing the exponent each time. So then we do the same thing here to find p double prime. So negative 2 times negative 40, positive 80, increase our exponent by 1. Negative 3 times negative 80, because remember you add a negative to the exponent when you bring it down in front. Negative 3 times negative 80, positive 240 here, increase your exponent to v to the fourth. Negative 4 times negative 120, positive 480, v to the fifth. Negative 5 times negative 160 is positive 640, v to the, let's see, this should be sixth actually here. This should be v to the sixth, because we increase our exponent by 1. And then, wait a minute here. 5 times 160, I think this is 4 times 160 here. 5 times 160, 5 times 100 would be 500, 5 times 60 is 300. This should have another 160 added on, that should be 800. So 800 v to the sixth, and then negative 6 times negative 5200 is 31,200, increase our exponent v to the seventh. Then we just need to plug in our discount factor 1 over 1.06, and we can evaluate p double prime at I. So I plug that in all the way along. My 640 here needs to change to 800. And then that's actually going to change our answer here. So instead of 21,843, let me just compute that real quick. And that gives us 21,963.54 with the correction. So then our convexity, p double prime over p double prime is the 21,963.54. And then p, our price was the 915.75. And if you divide those two, the ratio is 23.98. And without the correction here, it was actually closest to 23.85. So this would need to be changed to 98. And that's what I had meant. Yeah, which is D, not C. Okay, so there we actually calculated a convexity measure. So anything that you can price like this and write the price completely in terms of V, then you can use this derivative formula to calculate convexity by finding the ratio of P double prime over P. So when you think convexity, just remember concavity from calculus, which is given by the second derivative. Okay, the next example, we're going to look at this. We're going to look at that same formula, but symbolically. So symbolic answers here. So State Farm actually offers workers' compensation insurances for small businesses. Let's say that they're obligated to pay in the form of an annuity a claim that pays $10,000 on January 1 each year from 2015 to 2035. Which of the following would be an expression for the convexity of the claim as of December 31st, 2014? Okay, so this is basically saying at time zero because they're obligated to make that payment, that first payment the next day. Now be a little bit careful here. This is from time 2015 to time 2035. That's not 20 payments, that's 21 payments here. Okay, so notice that this is 21 payments. Right, from, because the payments here are January 1st at the beginning of the year. So the first 10 payments are the beginning of the first 10 years, which are 2015 to January 1st, 2024. And the end of the 10th year is December 31st, 2024. And we want to know which of the following is an expression for the convexity of the claim. Okay, so, well, if we, sketch out a timeline for what's going on here, time diagram, time zero, we are looking at the convexity of the claim on December 31st, 2014. Our first payment is on January 1 of 2015. So basically, our first payment is happening at time zero. So we've got a $10,000 payment here. And then we've got another one at time 1. And then we keep on going, and then 21 payments. That means that that last one here is going to happen at time 21, and time 0 is going to correspond to 1/1 of 15, and then time 21 is going to correspond to time 1/1/35. 21 years later. So convexity then, remember, is P double prime over P. And then our expression for P double prime, that was the sum of T plus 1, V to the T plus 2. Okay, that was from taking our derivatives when we expressed P just in terms of V. And then times the cash flow at time t, which all of our cash flows are the same. They're all 10,000. And then you divide by the price of the asset, that is the present value of the cash flows. So that's just going to be the sum of 10,000 brought back with v to the t. And our first cash flow is happening at time 0, so these are going to be summing from t equals 0. And so, I'm sorry, this is going to be 21 payments at time 0 to 21, and 20 years added on to 1/1/15 gives you 1/1/35. So this will be time 0 to 20, and then the same thing down here, time 0 to 20. Notice here that the 10,000 is a constant with respect to t, and this 10,000 is constant, so these guys could factor out and cancel. So those would actually cancel, so that's something to notice. So let's take a look at what we've got here. So we've got here 0 to 20, and I see t plus 1, 1 over 1 plus t. This is actually v, so this is v to the t plus 2. Downstairs 0 to 20, 10,000 v to the t. Okay, that looks good. Here 10,000 t minus 1, t v to the t plus 1. Okay, so, and this is starting at time 1 and going to time 21. So when t equals 1, this is going to be 0, this will be 1, and this will be 2. That's the same thing that happened over here. So actually these guys are equivalent. These two are going to be equivalent. Right? This is just a change of index. So if this starts at 1, ends at 21, which is 1 later here, and so your value of t is 1 higher, but then that was offset here by starting with a value that's 1 lower. All these values of t are 1 lower. Except in the denominator here, though, here we're starting at time 0, so we get v to the 0, so there's no discounting of the first payment, and that's what happens here. That first $10,000 payment has no discounting, but this one is discounted by v. Okay, so 10,000 brought back 1 period. So now these would have been equivalent. The top is equivalent. They would have been equivalent if down here instead of t they would have put t minus 1. So that guy's out. And then here t, we're summing up 0 to 20. We're doing t plus 1, t plus 2, 1 plus I to the negative t minus 3. This is the same as v to the t plus 3. So if you look at time 0, then this is going to be 1 times 2 times v cubed. And then on the bottom we're going to have a times 0 v to the first power. So you got a v cubed on the top and a v on the bottom. Even if we multiply top and bottom by 10,000 to put those in there, that first cash flow down here is getting discounted with a v to the first power, and that doesn't happen here. So this guy's out. And then here, t plus 1, t plus 2, v to the t plus 2. Well, notice here that we don't have the increasing pattern that we do down here. This is t plus 1 is 1 more, t plus 2 is 2 more. So this is t plus 1, 1 more, and then it doesn't go up by 2. So this numerator is not going to be a valid expression for p double prime. So that guy's out. And then here we've got the t plus 1, t plus 2 up there, and we've got the v to the t on the bottom. So if we put our 10,000s in here, then we'd look at, on the bottom again, we still got that issue. We're starting at t equals 1, so this cash flow on the bottom of 10,000, the first cash flow, gets discounted with v to the first. So the first term in this sum in the bottom is going to be 10,000 v, where in ours it's got to be 10,000. Okay, so this one's not going to work. And in the top here, we've got the same thing that in p double prime, we're starting at, when t equals 1, our first term is 1 times 2 times v cubed times 10,000. And down here, t equals 0, we've got 0 is our first term there. 0 to 20. Yeah, so this guy's out. Okay, so this has got to be choice A. Okay, now I want to look at the idea of immunization. And here what we want to do is, when we think of immunization, you get an immunization to protect you. And in actual science, that is still the idea of immunization. We're trying to have protection. Except it's not protection against a disease, it's protection against changes in the interest rate. Let me explain. So suppose that we buy some bonds, and we're going to use both the coupon payments from those bonds and the redemption value of those bonds to pay some anticipated future liabilities. So these could be, for example, payment of retirement benefits as an annuity. Then what we need to happen is, at time 0, we need the present value of all our cash inflows from the bonds, which again are coupons and redemptions, to equal the present value of these liability cash outflows, okay, which are going to be the fixed benefit payments each year. And that needs to happen at some fixed interest rate I0. Now, if the interest rate in the future doesn't change, then the cash inflows and the cash outflows are going to exactly match, and we're not going to have any problem. However, if rates do change, then there could be some adverse effect to our ability to make these liability payments. And let me illustrate here with a couple of scenarios that could happen and actually do happen in real life. So let's say that at a certain time during the period at which they need to use the cash inflows to meet the cash outflows, that their cash inflows at a certain time is actually less than the needed cash outflow. Okay, then what happens? Well, in order to meet their liability, they've got to sell some bonds. They've got to sell more bonds than just coupons plus redemptions that they had. Okay, well, if interest rates have not changed, then it's no big deal. They're going to receive, the anticipated amount of cash, what they planned on. If interest rates have decreased, then they're going to sell those extra bonds, and they'll actually be selling them at a premium, because remember here that as interest rates go down, so market rates have gone down, their bonds at a fixed higher rate are now more valuable, so the price of those bonds goes up. So they sell them at a premium. They're going to have all the needed cash to pay the liabilities and some excess. So we're in good shape. However, if interest rates have increased, okay, then what happens is they're going to have to sell those bonds at a discount. Because remember, if interest rates increase, so market rates have gone up, now their bonds at a fixed rate are less attractive. So their price has to decrease to make them more attractive to buyers. So that means that, maybe not at that point in time then, but eventually they could be short the cash to pay their liabilities. Not a good situation. Another possibility is that at a certain time the cash inflows, coupons plus redemptions, is actually going to be greater than the needed cash outflow. If that happens, then they've got excess cash that they need to invest. If rates are not changed, then we don't have a problem. They just reinvest everything at the same rate, and they make the anticipated liability payments just like they would before. If interest rates have increased, then they're going to reinvest here at a higher rate. Okay, that's great. That means that they're going to get a greater return at that higher interest rate. So they're going to have the needed cash that they need to pay those liabilities and some leftover. That's great. But what if interest rates have decreased? Then that means that they're going to reinvest their excess cash at a lower rate than what they anticipated. So that means again that they're going to be eventually short the cash to pay those liabilities. Not a good situation. So the short of this again is, your moral is that unless cash flows exactly match here the cash outflows that are needed between their assets and their liabilities, then changes in the interest rate could adversely affect the ability of this company or entity to pay their liabilities on time. So immunization then refers to the process that we're going to use to protect companies or financial institutions against these adverse effects of changes in interest rates. So it's immunization against the adverse changes from interest rates, either going up or going down depending on what your situation is. And the particular kind of immunization that we're going to look at is what's called Redington immunization. And this is named after the actuary about 1950s when he did his work. And to do Redington immunization, you make three assumptions, or you try to ensure that three things happen. The present value of your assets has to equal the present value of the liabilities at this interest rate, I0. And then also you insist that the duration of your assets should equal the duration of the liabilities. And by duration, we could mean either MACD or mod D. And then you lastly insist that the convexity of your assets is greater than the convexity of your liabilities. And what we'll see is that these last two conditions here, those two are the ones that are going to ensure that small changes in the interest rate give you a net increase in the present value of assets over liabilities. Okay, so if your liabilities go up but your assets go up a little bit more, we're okay. If your assets go down but your liabilities go down a little bit more, we're okay. So that's what we're talking about by saying a net increase here. So that's what we want to ensure. So one alternate definition using these three properties here. First, if you say the present value of the assets is equal to the present value of the liabilities, that's at time 0. That's saying that the price of the assets equals the price of the liabilities, where by price here we're talking about PV. And actually when we say the present value of the assets, we mean not only the value of the assets themselves, but all the cash flows that come from the assets. And the same for the liabilities, present value of all the cash flows that come from the liabilities. Second condition here, if we insist that the duration of the assets is equal to the duration of the liabilities, well, we could use either MACD or mod D. Let's use mod D. So remember that the modified duration is the negative of P prime over P. That was our definition. So if we're insisting that the duration of the assets is equal to the duration of the liabilities, then that's saying negative of P prime of A over P of A has to equal the negative of P prime of L over P of L. Now if we just multiply both sides by -1, that means that the ratio, these relative rates are the same. But then from number 1 we know that P of A equals P of L. Okay, so since the present value of the assets equals the present value of the liabilities, that means if you multiply both sides by P of A or P of L, that these guys are going to cancel out, and you're just going to get that P prime of A has to equal P prime of L. So this is, look at the present value of the assets as a set of cash flows, write it in terms of V, and this derivative, this prime here, since we're using mod D, is derivative with respect to I. Okay, so those derivatives are equal to each other. And then thirdly, to say the convexity of the asset cash flows is greater than the convexity of the liability cash flows, that's saying that P double prime of A over P of A, that's the convexity of the assets, it has to be greater than P double prime of L over P of L. That's our definition of the convexity of the liability cash flows. Okay, but again, these denominators are equal to each other. So from condition 1, so since the present value of the asset cash flows equals the present value of the liability cash flows, again, this reduces this condition to say that it means P double prime of A has got to be greater than P double prime of L. So these three conditions here then, the present value of the asset and liability cash flows have to equal, their first derivatives have to be equal, and then their second derivative of the asset cash flows has to be greater than the second derivative of the liability cash flows. What that's telling you, those three conditions together, what that's telling you is that if you look at the function P of I, okay, so this is the present value of the cash flows written in terms of the interest rate, that thing has a relative minimum at that current interest rate, which is I0. And why is that? Okay, well, this is saying that the derivatives are equal to each other. Okay, so if the derivatives are equal, then you've got a horizontal tangent. And here this is saying that the concavity is positive. Actually, the net derivative is 0 here, and the net concavity is greater than 0. So if your derivative is equal to 0, then you've got a horizontal tangent. And if your concavity is positive, then you've got a minimum. That's actually second derivative test is what they're using there. Right? You've got this type of situation. Here's your relative min, that's at I0. P prime is equal to 0, that's your horizontal tangent. P double prime is greater than 0, so you've got a relative min. You have to look at it in terms of net, though. So in terms of net flows here, the net present value, we'll call that P, is the present value of the assets minus the present value of the liabilities. Or if you look at the individual cash flows, A sub T being an asset cash flow and L sub T being a liability cash flow, if you take the present value of each one of those net cash flows, asset minus liability, and bring them all back, that's what P is, the net present value. Okay, then this first condition here is just saying that the net present value, P, has to equal 0. Second condition, the derivatives P prime of A and P prime sub L are equal. That's just saying that P prime equals 0. Okay, because net present value is P sub A minus P sub L. So the derivative of net present value is the derivative of the first term, P prime of A, minus the derivative of the second term, P prime of L, and these guys are equal, so that derivative equals 0. So there's your derivative equals 0. And then this third condition here, to say that P double prime of A is greater than P double prime of L, well, if we take the second derivative of P, where P is the net present value, then we just take the second derivative of the first term, P double prime at A, minus the second derivative of the second term, P double prime at L, and since P double prime at A is greater than P double prime at L, this is greater than 0, but that is actually equal to this guy, or this one. Okay, so your second derivative of your function is greater than 0, so it has to be concave up at the point relative minimum. Okay, so this is really calculus in disguise. Now, actually, these three different definitions of immunization, it just depends on which author you look at as to what their definition of Reddington immunization is. This is a more general concept, but when we get down and writing in terms of net present values, then we actually get to see the calculus that's going on. But they all mean the same thing. All right, let's put it to work. So in this example, we've got a company and they buy a 5-year zero coupon bond that matures for $5,000, and they're going to use it to make 2 liability payments. Their first payment's going to occur in 2 years, and their second payment is going to occur in 6 years. We want to compute the amount of the payments to ensure that Reddington immunization occurs at a 6% effective annual rate. All right, well, let's let x equal the amount of the payment that happens in 2 years and y equal the amount of the payment that happens in 6 years. Then the first condition says that the present value of the asset liabilities cash flows has to equal the present value, of the asset cash flows has to equal the present value of the liability cash flows. And that's at I equals 0.06. So the asset cash flows, well, this bond, you just purchased one zero coupon bond, so you've got one asset cash flow. $5,000 is going to come in when that thing matures in 5 years. Well, this is the present value of that one cash flow. Okay, so time diagram. Let's put this is 0, this is time 5, and then we'll have time 6 out here. And you had another cash flow at time 2. Okay, so we've got, let's put the asset cash flow above the line. So we've got the $5,000 asset cash flow, and then we've got our two liability cash flows. We're going to let X be the cash flow at time 2 and Y be the cash flow at time 6. So the first thing is we need the present values of those cash flows to equal each other. Well, the present value of this cash flow is just 5,000 discounted 5 years. So that's 5,000 v to the 5th has got to equal the present value of these two cash flows. So cash flow of X gets brought back 2 years. So XV squared plus this liability cash flow of Y gets brought back 6 years. So Y times v to the 6. And then notice here we've got a common factor of v squared all the way across that we can divide out. So if we divide v squared, divide by v squared here, all the way across, then we get 5,000 v cubed has to equal x plus y times v to the 4th. Okay, so the first condition of Redington immunization gives this equation. Okay, let's look at the second condition. P prime sub A has to equal P prime sub L. Okay, remember our derivative here, v to the n, the derivative of that is negative n, v to the n plus 1. Okay, and here is our P sub A. So if we differentiate that, negative 5 comes down in front. Times that 5,000 is going to be 25,000. So I'm going to go ahead and just write that. So negative 5 times 5,000 will be negative 25,000. V, increase the exponent, 6th. And that has to equal the derivative of these cash flows. So 2 comes down in the front with a negative. Times, let's go ahead and put the v cubed out in front, and then times x. And then the derivative of v to the 6 with respect to I is going to be negative 6v to the 7th, and then times our cash flow of y. So that's the second thing that has to happen. Notice again we've got a common factor here that we can cancel out all the way across. So let's see, we've got a v cubed, so we can cancel v cubed all the way across. And that's going to give us negative 25,000. V cubed is going to equal, these v cubed will cancel, negative 2x. And then minus 6, cancel 3 v's, we've got 4 left, so v to the 4th y. And then all these terms are negative, so multiply through by negative 1 on both sides. So now what we have is we have a system of equations with 2 variables and 2 unknowns. Okay. Let's see. Oh, also notice here we've got a common factor of 2 that we can divide off on both sides. So 2 goes into 25,000, that'll be 12,500. These 2's cancel, and here 2 goes into 6 3 times. So now we've got a system of 2 equations and 2 unknowns. So this second equation can be written as 12,500 v cubed equals x plus 3v to the 4th y. And then this first equation down here, 5,000 v cubed equals x plus v to the fourth y. So I wrote it so that our coefficient is out in front and our variable comes afterwards. And now these are all set up to do elimination, so just subtract the two equations. 12,500 minus 5,000 v cubed gives 7,500 v cubed. X minus x gives 0, so those guys cancel out. 3v to the fourth y minus v to the fourth y leaves 2v to the fourth y. So now we've eliminated x and we've got it just in terms of y, so divide both sides by 2v to the fourth here. And we get y is 7,500 v cubed over 2v to the fourth. These three v's will cancel all but one v on the bottom. And 2 will go into 7,500 two times. 2 canceled into 7,500 will leave us 3,250. So we get 3,250 over v. And dividing by v is the same as multiplying by 1.06, because here our I is 0.06. And that will give us 3445, rounded to the nearest penny. So that just turned out, this is really 0.00. So that one turned out nice. So we have to purchase, the second payment here. It's not what we have to purchase, but the amount of second payment that we have to make from that is going to be $34.45. And then to find x, all we have to do is go back to our equation here. And if we bring the v to the fourth y over as a negative, then we'll have x is 5,000 v cubed minus v to the fourth times our y. And then we know what y is. It's 34.45. So if we do the plugins here, v is 1 over 1.06. That gets cubed here, fourth power here, and plug in y. And we get 1469 for our x value. So here's our x, and here's our y. Now we want to verify the third condition. Even though we've already solved for x and y here, we better make sure that the convexity of the asset cash flows is greater than the convexity of the liability cash flows, because that's what's going to ensure that this point is a minimum and not a maximum. Okay, so what's p double prime at A? Well, p prime at A, that's the derivative of the asset cash flows. Okay, and that is this left-hand side right here. So we need to do one more derivative there. So 6 comes down as a negative. Negative 6 times negative 25,000 is going to give us 150,000. And then we increase our exponent by 1, so v to the 7th. So then that's 150,000, and we plug in our discount factor 1 over 1.06, and this should be a 7th power. Okay, and that's going to change this answer a little bit. So actually this is going to end up being 99,758 is actually what that's going to be. So this is 99,758.57. And then we need to find the second derivative of the liability cash flows and make sure that that is less than the 99,758. So that's going to be the second derivative. We need one more derivative of this expression right here, negative 2v cubed x minus 6v to the 7th y. So negative 3 times negative 2 is going to be a positive 6. Increase our exponent by 1. V to the 4th times x, and then negative 7 times negative 6, positive 42, v to the increase the exponent 8th times y. So there's our second derivative of the liability cash flows. And if we do the plug-in in that we need to do here, with v is 1 over 1.06, we'll have 6, 1 over 1.06 to the 4th, times our 3445, and then plus 42, 1 over 1.06, this should be an 8. Times our 1469.33 from right here. So we've brought down our x and y values. And if you do the calculator work there, you need to adjust that one. That actually gives us 55,091 and 36 cents. But what's important here is that this second derivative is greater than this one. Okay, so we do have the second derivative of the asset liability cash flows is greater than the second derivative. Second derivative of the asset cash flows is greater than the second derivative of the liability cash flows. So this did check out. So that means that we do have, so that implies that we do have Reddington immunization. All right, let's look at another example here that's a little bit more involved. So here we've got an insurance company and they need to pay out $100 annually in the form of a 20-year annuity immediate. And to generate those cash flows, the company buys 2 zero-coupon bonds to fund the payments. So the first bond matures in 5 years and the second in 15 years. So these are zero-coupon bonds, so they're only going to have 2 asset cash inflows, but they're going to have 20 $100 cash outflows. And then these bonds are going to be purchased so that they yield 8% effective annual rate. And we want to know what face amount for each bond should the company buy. So this effective annual rate would actually, the yield on those zero coupon bonds would actually be determined by whatever current interest rates are now. So by deciding, by knowing what current interest rates are, then they can find what the yield on the bonds will be. So this is determined for us in this particular example. We didn't have to compute it. So we want to know what face amount or what dollar amount of each bond should the company buy so that they'll be immunized against any changes in small changes here. And that's key there, small changes in interest rate. And if they do that, do we have Reddington immunization? So here we want to try to go through the same 3 conditions for Reddington immunization and see if all 3 hold. Well, let's let X be the face amount of the 5-year bond, and let's let Y be the face amount of the 15-year bond. So these are going to be the face amounts instead of liability payments again. So if we draw our time diagram here, we've got a 20-year period here. And we are going to have, let's put our assets above the line. So we are going to have an asset mature at 5 years. So that's going to be in here somewhere. And that's going to be the face amount X. And then we're going to have another asset mature at 15 years. So that'll be about up here. And that's going to be the face amount Y. Those are going to be our cash inflows. And then our cash outflows are going to be $100 a year, and this is an annuity immediate, so $100 at the end of every year. for 20 years. So our last cash outflow is at time 20. All right, so what has to happen? Present value of the asset cash flows has to equal the present value of the liability cash flows. So the present value of x at time 0 is going to be x brought back 5 years with v to the 5th, plus the present value of y at time 0 is going to be y brought back with v to the 15th. And then this is just a constant annuity immediate, and the present value of an annuity immediate of $1 is going to be A angle N. Well, this is $100, so this is just going to be 100 A angle N, and N is 20, so it's going to be 100 A angle 20. So that's our first condition. And this is going to be, again, at the yield of I equals 0.08. And so if you compute v to the 5th, okay, so I equals 1.08, so our discount factor is going to be 1 over 1.08. So then if you compute v to the 5th to the nearest and round it to 4 decimal places, you get 0.6806. So that's our coefficient of x. And then v to the 15th is 0.3152, that's our coefficient of y. And then 100 A angle 20, if you compute that at I equals 0.08, you get 981.8147. So it kept 4 decimal places of accuracy. So here we've got one equation and 2 unknowns. And that happened before. We're looking for another equation and 2 unknowns. So the second condition of immunization is that the derivatives of the asset and liability cash flows have to equal each other. All right, so here's our asset cash flows. And our liability cash flow, well, we have to rewrite that one a little bit. First, let's look at the asset cash flows. That one we can do easily. So a -5 is going to come down in front here, and it'll be v to the 6th. So this will actually be -5v to the 6th, and then times our x if we put all of the coefficients out in front, and -15v to the 16, so minus 15v to the 16 times y. So that's the first derivative of our asset cash flows. And then that's got to equal the first derivative of our liability cash flows. So this is going to be equal to, and this is derivative with respect to I here, because we're using modified duration. So A angle 20, 100 A angle 20 is going to be the derivative of 100. And then angle 20 is just going to be, this 100 is brought back with v. The next one is brought back with v squared, and so on up to v to the 20th. So this will be v plus v squared plus ... up to v to the 20th. And we wanted to write it this way so that we can use this formula. The derivative with respect to I of v to the n is -n v to the n plus 1. Okay, so the constant 100 will factor out of the derivative, and then also all of these exponents get brought down with a negative. That is this negative right here. So we can actually pull a negative on the outside along with the 100, and then we can differentiate each one of these guys with a positive. So then positive 1 comes down, v, increase your exponent, so v squared. 2 comes down, v cubed, so plus 2v cubed, all the way out to, last one is going to be 20 down in front, and then v to the 21. And then notice here, I've got, well, I've actually got a common v squared, but I'm only going to pull out a v. So this is going to be -100v. And then what I'll have left is going to be v plus 2v squared. And then the next term is going to be 3v cubed. And then plus all the way up to last term will be 20v to the 20th. And then this should look familiar to you. That is the present value of the increasing annuity for n equals 20. So this is negative 100 times V times IA angle 20. Again, at I equals 8%. And if you do the work to compute IA angle 20, you get 78.9079. And our negative 100 is here. And then multiplying by V is dividing by 1.08. So that gives you negative 7306.2870. And that's the right-hand side of our linear equation. And this is the left-hand side. If we compute negative 5V to the 6, we get negative 3.1509. Negative 15V to the 16 is negative 4.3783. And then I brought my negative 73 back down on the right. So now we've got two equations here and here in two unknowns. Now these are a little messier equations than what we had before, but still solvable. So I brought those two equations down here. Now I'm not so sure I want to do elimination on these. It looks like it could be kind of messy, so I'm thinking, why don't we do substitution? Okay, so why don't we take this first equation, solve it for y, and substitute in the second equation. So here's our first equation. I brought it down. If we solve this for y, we want to bring this term over as a negative. So we'll have the 981.8147 on the right-hand side, minus this term will come over as a negative. So this guy's coming over. 0.6806 x, and then that'll leave us the 0.3152y, and then divide both sides by 0.3152. So there's y solved in terms of x, and then we want to take this guy and plug it into the second equation. So the second equation we want to plug in for y right here. We're plugging this expression in. So here's my 3.1509x, 4.3783y, 4.3783, and then here's my y solved above. And then if you do the algebraic simplification here, oh, and then this is set equal to the right hand side up here, which is 7306.287. And then if you do the algebraic simplification on this equation and then combine your x terms, you get an x term in here and then an x term here after you do the multiplication, after you distribute, then you get 13637.9419 minus 6.3030x is 7306.28. So now we've just got an equation in one variable. We can solve this thing for x. So bring this term over as a negative and then divide off this coefficient. So then your x is going to be 7306.287 minus 13637.9419. So that's this coming over as a negative. And then divide off this negative coefficient. And divide by negative 6.3030. And that gives you 1004.55. And then once you've got x, you can plug back into either equation for y, but we've already solved this one here for y. So just take and plug in our x right there. So this 1004.55 gets plugged in right there, which is right here. And do the arithmetic there, the calculator work, you get 945.81. Okay, so now we've got two amounts. We've got our x, which is 1004.55, and we've got our y, which is 945.81. So now let's check these second derivatives and see if we've got Reddington immunization. So we have a solution. Do we have Reddington immunization? Well, our second derivative on the asset cash flows, that's not too bad to do. And go back up and take a look here. Our first derivative is right here. So we got to do one more derivative there. So that's going to be a negative 6 times a negative 5 is going to give positive 30 v to the 7th x. So this is positive 30 v to the 7th times x, and then negative 16 times negative 15 will give you a 240, so positive 240, and then we want to increase our exponent here, so v to the 17th times y. And now we can just plug in for v, x, and y and evaluate the second derivative of the asset cash flows. So 1 over 1.08 7th power, 1 over 1.08 17th power, and then I plugged in my x and y. We get 78,993. Now, the liability cash flows, that one is a little bit more work. So what we're doing is we're taking one more derivative of this expression right here. And when we do that, we don't get a nice pattern. We don't get a nice annuity like the increasing annuity. We get something really ugly. And I actually had to do quite a bit of computational work and even use a computer algebra system to evaluate. But when I did, if I did the derivative with respect to I of this is our expression for the first derivative of the liability cash flows, and then I evaluated it at 1.08, I got 86,088. Okay, but notice this is greater than the asset the second derivative of the asset cash flows. Okay, we want it to be less than. Okay, so this means that we don't have Reddington. Okay, we don't have Reddington immunization. So what this is saying here is that that second derivative is not positive. It's not concave up. It's negative. It's concave down. Okay, so we actually have a relative maximum instead of a relative minimum. Okay, now this, just a couple of notes here. This expression would be nearly impossible. It's very, very tedious to do on a BA2+. So if this was an exam question, we would actually expect the exam writers to do something reasonable, like the first example that I did. Especially if they're asking you to show that there's Reddington immunization, or that Reddington immunization is going to occur. So notice here we actually got a solution, but we didn't know that our solution was immunizing. We didn't know that it was a minimum unless we did this last step. So if you're going to be showing Reddington, then we can assume that the exam writers are going to make sure that that's true. And in that case, you really shouldn't need to check this last step. Now, what that means then, if we go back up here and we look at the question, okay, well, what face amount of each bond should the company buy to be immunized against small changes? Well, the answer that we got, that is the amount that they should buy. The only problem is that it's not providing proper immunization. So we proceeded in the correct manner, but we couldn't get Reddington immunization here. So the author took a similar example, and they illustrated a case where you didn't have Reddington immunization. But actually what happened was you had immunization for essentially all practical interest rates. Now, even when you do get a positive derivative there, it's actually only a local minimum. When you get a positive second derivative, it's not necessarily a global minimum. So when you do get immunization to occur, and here we don't have immunization, when it does occur, though, it's only true for small changes in the interest rate from whatever your base rate was. In our case here, it was the 8%. not necessarily for large ones. Although in an example that the authors gave, they had showed that they had a relative minimum, and it actually ended up being good from all interest rates from 0 all the way up to 205%. So for all practical purposes, that was, almost full immunization. Okay, Reddington immunization only immunizes with small changes. So even if we got the second derivative to be positive, then that's only going to mean that we're insured against small changes in the interest rate, not necessarily large changes. So that's just something to keep in mind. And then a general note, we defined our duration and convexity here when we did. We assumed that the yield curve was flat, and then we used that same interest rate to to compute the present value of all of our cash flows, no matter what the time remaining was. And then also when we developed Reddington immunization, we assumed that the changes in the interest rates occurred in parallel shifts when we took our derivatives. In other words, the rates changed by the same amount for all of the cash flows. No matter what the time remaining to the cash flow was. That does not happen in real life. Very rarely would that happen in real life. But in order to make reasonable, to do reasonable test questions for the exam, we've got to assume that this happens. So we're going to assume that we've got a flat yield curve. Okay, our interest rate is the same across all durations here, and that when changes do occur, that they're going to occur in parallel. Okay, they're going to the rates are going to change by the same amount for all of the cash flows. So just something to be aware of, that what we're looking at is a model, and we've made some simplifying assumptions in our model. And then, in order to deal with a real life situation, then our model is going to be an approximation, and then we'll make adjustments to our model to try and get a better approximation. In fact, that's actually what we did when we went from using modified duration to estimate changes in price to using convexity to estimate changes in price. We improved our first model by looking at the second order approximation instead of the first order Taylor approximation.